Hello everyone, welcome back to our channel. Today we're going to do some more virtual trigonometry and we're going to focus on trigonometric identities. There are a lot of trig identities and we're not going to do them all today. We're just going to do a few that are the most common and probably the most useful, but there are a lot more out there. The first group is a group of identities that are pretty straightforward. You've seen them before. I'm just going to remind you of them and know that you can always use them anytime you're trying to simplify an expression. So some of these are the reciprocal identities. So for example, cosecant of theta is the same as 1 over sine of theta. Right? Can you see that over there? I don't know. Let's try a different marker. This also means 1 over cosecant of theta is the same as sine of theta. Right? We know this.
And then we can do the same thing for secant. 1 over secant of theta is equal to cosine of theta, and 1 over cosine of theta is equal to secant of theta. And 1 over tangent of theta is equal to cotangent of theta. 1 over cotangent of theta is equal to tangent of theta.
All of the reciprocal identities, we've worked with these before when we defined cosecant, secant, and cotangent. But these are all identities that are true and can sometimes be helpful when we want to simplify identities. Or simplify trig expressions. Alright, a couple other basic ones are based on the graphs of trig functions. So we talked briefly about how the sine graph is an odd function. It has odd symmetry. The cosine graph has even symmetry. The tangent graph also has odd symmetry. So because the sine graph has odd symmetry, we can say if we have, usually that means sine of, let's say, theta, it will be the same as if you had negative sine of negative theta, right? If it's something has odd symmetry, it's reflected over the origin or over both the x and the y-axis. So if you make both the input and the output, you make the x and the y both negative, you'll come back to the same point that you had before. So if we just want sine of our negative angle, its relationship to the sine of the positive angle will just be negative sine of that positive angle. Right? So like let's say we had sine of negative pi over 2, that will be the same value as negative sine of regular pi over 2. Which you can validate. Sine of negative pi over 2, negative pi over 2 is at the same place as 3 pi over 2 on our unit circle. Sine of negative pi over 2 is negative 1. Negative sine of pi over 2, sine of pi over 2 is 1, negative 1. Negative 1 equals negative 1. Check. We can do the same thing for tangent, because tangent also has odd symmetry. So tangent of negative theta is equal to negative tangent of theta. Okay, cool. So we have sine of negative theta is equal to negative sine of theta. Tangent of negative theta is equal to negative tangent of theta. And then cosine is not quite the same, right? Cosine is an even function. So when we do cosine of negative theta, that's just going to be the same as cosine of positive theta, because it's even. So if you reflect it over the y-axis, it's still going to be the same. If you make the x's negative and leave everything else the same, you're going to have the same graph. So, for example, this one for cosine could be like cosine of, let's do negative pi over 4. That's going to be the same as cosine of pi over 4. Cosine of negative pi over 4 is in the 4th quadrant, so it's going to be at the same place as 7 pi over 4. Cosine of 7 pi over 4 or negative pi over 4 is going to be root 2 over 2. Cosine of regular pi over 4 is also root 2 over 2. So these three are our symmetry or our odd, even identities that can be helpful if we want to make anything not negative or show the relationship between any negative angles. Okay, the next one is tangent and relating tangent to sine and cosine. I showed this in a video a little bit earlier that was just on a blackboard, but we can see that tangent, right, of theta is equal to opposite over adjacent. We know that from SOHCAHTOA, right? If sine of theta is equal to opposite over hypotenuse, and cosine of theta is equal to adjacent over hypotenuse, that's kind of a P, then we can say that tangent, right, we can say is going to be opposite over hypotenuse all over adjacent over hypotenuse. And these hypotenuses will cancel out, because it's when you divide by a fraction, you really multiply by its reciprocal. And this is the same as sine over cosine. We can also see this a little bit more clearly on the unit circle, where our hypotenuse or our radius is 1. Here's our angle. This is our y value, also our sine value. This is our x value, also our cosine value. And then our tangent is just y over x, opposite over adjacent, or sine over cosine. This also means that cotangent will be cosine over sine, because it's the reciprocal of tangent. Thumbnail. Okay. The next one starts to get into some more fun ones that we haven't really seen before. They're a little bit different, kind of funky, very exciting, very useful. So this next identity is what's called the Pythagorean identity. The Pythagorean identity is very similar to what you would assume, Pythagorean theorem, and that's what it's going to use. So we can relate sine and cosine through this triangle and say that our x squared plus our y squared, right, our one leg of our triangle plus our other leg of our triangle equals our hypotenuse squared, otherwise known as cosine squared plus sine squared equals 1. Cool, so cosine squared plus sine squared equals 1. 1 squared is just 1. That is the main Pythagorean identity. But Ms. Strudwick, you may ask, that's only in the unit circle when there's a hypotenuse of 1. Will that always work? Yes, it will always work. But I can show you with a different hypotenuse, or with just letters, if you don't believe it. So, let's draw a triangle, a right triangle, and this could be any right triangle. I'm going to call my hypotenuse H, and I'll just call these A and B. And here's my angle. Okay, so B is my opposite, A is my adjacent, H is my hypotenuse. So, as we know, right, A squared plus B squared equals H squared. If I divide the whole thing by H squared, by my hypotenuse squared, and I can do that because if I do it to one thing, I just have to do it to everything to balance out the equation. I'm not changing the value of the equation at all. But now, by properties of exponents, I can take out my exponent if it's the same on the top and the bottom. So now, I can make this A over H all squared plus B over H all squared equals H over H, or 1 all squared. A over H, adjacent over hypotenuse, that's cosine, cosine squared. b over h opposite over hypotenuse is going to be sine squared of theta. H over h is just 1, squared is still just 1. So we can start with that Pythagorean identity that we just showed. I know I wrote it cosine squared plus sine squared equals 1, but I'm going to write it sine squared plus cosine squared just because I like how that sounds better. Sine squared plus cosine squared equals 1. And this is kind of our main Pythagorean identity. But we can rewrite this in terms of our other trig functions, because there's 3 other trig functions, actually 4 other trig functions we haven't talked about yet. This is only in terms of sine and cosine. But I can divide everything by, change colors. I'll divide everything by cosine squared. Okay, and now sine squared divided by cosine squared is sine over cosine squared, or tangent squared of theta, plus cosine squared over cosine squared is 1, equals 1 over cosine squared, or 1 over cosine all squared, which is going to be secant squared of theta. So that's one alternative to the same Pythagorean identity. So there's actually 3 versions of our Pythagorean identity, and we'll do the 3rd one in a second. So there's sine squared plus cosine squared equals 1, and now we also have tangent squared plus 1 equals secant squared. You can probably guess the other one. Instead of dividing all this by cosine squared across the board, we're going to divide it by sine squared across the board. So if I divide everything by sine squared of theta, sine squared of theta, sine squared of theta, now I'm going to get my 3rd and final version of my Pythagorean trig identity. Sine squared over sine squared is 1, plus cosine squared over sine squared, or cosine over sine all squared, which is cotangent squared of theta, equals 1 over sine squared, or 1 over sine all squared, which is going to be cosecant of theta squared. So there's 1, 2, 3 versions of our Pythagorean identity. And you may notice that I've been writing the squared right after the sine and before the theta. That's just common notation. So, for example, we don't write the squared after, but what this means is if we have, let's say you want to do sine of theta all squared, the way we write that is sine squared theta, and that distinguishes from sine of theta squared, because if you wrote that, people think you mean the angle squared, not the actual whole value. So sine squared of theta is the whole thing squared. Sine of theta squared is sine of theta squared. So that's just notation. Woohoo! Alrighty. So pause the video and try to simplify this side of the expression, the left-hand side of the expression, to just be cosecant of theta using some of the identities we just talked about. So it reads cosecant of theta times cosine squared of theta plus sine of theta equals cosecant of theta. So just work on the left-hand side and see if you can change some of these things so that they reduce and are only equal to cosecant of theta. Okay, so these are my first 2 steps. I changed cosecant of theta to just be 1 over sine of theta by its reciprocal property. So I have 1 over sine of theta times cosine squared plus sine of theta. And then I just multiply these 2 together. So I have cosine squared theta over sine theta plus sine theta. So now, what I'm going to do is I'm going to multiply by sine theta over sine theta. right? And I can do that because sine over sine is just 1. So I don't have to multiply to the whole thing. I don't have to multiply to more than one part. I'm just multiplying it to the plus sine theta. And the reason why I'm doing that is you can look at what the answer is supposed to be to give you a hint. I know that I want it to be just cosecant of theta. And I know cosecant is 1 over sine. I have a sine in the bottom over here, so that's kind of giving me a hint, like, all right, so I'm on the right track. I have sine in the denominator, but that means I need the numerator to be 1, and I need there to be nothing else that I'm adding. We just talked about the Pythagorean identity, cosine squared plus sine squared equals 1. That's helpful. But I'm thinking, okay, I have the sine in the denominator, and I have a cosine squared up top, so I need to figure out a way that I'm going to add sine squared to this bit in the top in order to get rid of it and change it into a 1. And I have this plus sign hanging out by itself, so when I multiply it by sine over sine, I'm going to get another sine in the denominator, and I'm going to get a sine squared on top, which is huge. So now I have cosine squared of theta over sine of theta plus sine squared theta over sine of theta equals cosecant. And now I can add with properties of fractions because they have a common denominator. Chill. So now I have cosine squared plus sine squared all over 1 sine of theta. And I'm pretty much done. Cosine squared of theta plus sine squared of theta, Pythagorean identity, that equals 1. So now I have 1 over sine of theta, right? And that does, in fact, equal cosecant. Huge. That was fun. So this whole thing on this left-hand side, all simplified to just be cosecant of theta. Cool. Thanks so much for tuning in to another fun virtual trigonometry lesson on our channel. Subscribe, like, favorite, share, text, tweet, etc. Have fun doing some more trig. Woo!